Okay, let's dive in. There's this huge paradox, really, sitting right at the heart of how we understand physics.
Hmm.
We rely on things like mass, force, to be super precisely defined. But the very field that gives mass to almost everything, well, it's defined using a word that's just incredibly slippery.
Yeah, it means like three completely different things depending on the context. It's a real linguistic mess, isn't it?
Totally. And that word is scalar. So how can one little word mean, just a simple number with no direction, like the temperature? That's kind of definition A.
Right, your basic temperature reading, no direction needed.
But then suddenly it pops up describing an action, like an operation in math class, right? Scalar multiplication, where you take a number and you, like, stretch a vector.
Exactly. Definition B, the operation, the doing something, not the value itself.
And then, and this is the mind bender, it shows up in this, like, massively profound context. The scalar field, the Higgs field specifically.
Yeah.
This fundamental map covering the whole universe, telling particles how to get mass.
Mhm.
So if a scalar is an operation, like stretching, how can the universe be a field of stretching commands? It doesn't make sense.
It sounds completely contradictory. And that confusion, that mix-up between a value, an operation, and this physical map, well, that's what trips up almost everyone when they first encounter quantum field theory.
Yeah, it feels like someone just messed up naming things. But actually figuring out this confusion, untangling it, that's the key.
It really is.
If we can carefully separate the shortcuts in language from what physicists really mean, the formal definitions,
Mhm.
we don't just unlock what the Higgs field is. We get this beautiful, logical reason why it absolutely must be what we call a spin zero thing.
And that leads directly into classifying reality itself based on, believe it or not, just how things behave when you rotate them. Geometry.
That whole rotation perspective, how
Mhm.
things look, how they transform when you change your point of view.
That's where all the deep physics is hiding.
Yeah.
Yeah.
So today, we're going deep. We're going to resolve this fundamental confusion around scalar and field, and hopefully you'll come away with a really profound grasp of the universe's grand structure, classified by this thing called spin. Spin 0, spin 1, and spin 12.
That's the plan.
And that, everyone, is our mission for this deep dive.
Sure.
Welcome along. We are genuinely so grateful for the amazing response we've been getting to the show lately.
It's been fantastic.
Seeing people share these discussions, talking about them, it really means a lot. And honestly, it keeps us fired up.
It really does. It's inspiring. And speaking of growth and engagement, we actually have a quick sort of internal note, a bit of housekeeping, if you will, for you, our dedicated listeners.
Yeah, so our brilliant marketing team, they ran some numbers recently, and they found something pretty interesting. Turns out, only about 2% of the people listening right now have actually, hit the subscribe button.
Which is kind of wild, right? It means we have this incredibly engaged core, which is amazing, but there's this huge group out there that enjoys the deep dives, but hasn't sort of made it official yet.
Yeah, and the marketing folks, they're really pushing us quite hard, actually, to evolve the show.
Yeah.
They think, and honestly, we kind of agree, that to reach that wider audience, we really need to bring in video.
Makes sense. Especially for some of the stuff we talk about. Visualizations, diagrams. I mean, imagine trying to explain the Dirac belt trick later without seeing it. Video would make these concepts so much clearer.
Oh, definitely. And believe me, we want to do that. We really want to add that visual layer. But, well, it's the classic chicken and egg problem, isn't it?
Mm-hmm.
To make really good, professional-looking video content that, matches the depth we go into here. That takes some pretty sophisticated tools. And those tools, well, they cost money.
Yeah, and we've been looking into this quite a bit, researching the sort of cutting edge in creative tech. And one tool we're really excited about specifically is the Mosaic AI video editor.
Right. That's mosaic.so. https.mosaic.so for anyone curious.
And the reason it's so cool is that it automates a ton of the creative heavy lifting. Like, we could basically just feed it the link to our finished audio deep dive on YouTube.
Oh, yeah.
And it automatically generates really nice, relevant AI brol footage, visuals, graphics, stuff that matches the content. It helps streamline the whole process.
It sounds amazing. Like the ultimate tool to speed things up but keep the quality high.
Mm-hmm.
But, and here's the catch, We need to hit 1,000 subscribers. That's the magic number to unlock the budget we need to actually get Mosaic AI and integrate it properly.
So here's the ask. If you're getting value out of this, if you enjoy these deep dives, maybe do 2 quick things for us.
Please, first, maybe share the show in your WhatsApp groups, on social media, wherever you think people might appreciate this kind of discussion.
And second, probably the most important one right now, just take a second and hit that subscribe button wherever you're listening. It costs nothing, but it helps us massively towards that 1,000 goal.
Help us get the funds from Mosaic AI so we can bring these conversations to life visually. We really, really want to do videos for you.
Let's make it happen. Okay, enough housekeeping.
Absolutely. Let's dive back into the physics puzzle. Drum roll, please.
Okay.
Right, physics basics. Let's start right at the beginning, high school level stuff, just to get the intuitive ideas on the table before we kind of blow them up with the formal definitions.
Good plan. Vector versus scalar.
Vector, what is it?
Simple enough to start. A vector quantity needs 2 bits of info. One is its size, its magnitude.
Like how fast?
Right, and the other is its direction. Where's it pointing?
So the classic example is always velocity, right? If I'm driving, saying 70 miles per hour isn't enough.
Nope. Gotta know where.
70 miles per hour north.
Yeah.
That combo, magnitude and direction, that's your vector.
Perfect. And the scalar, intuitively, is just the opposite. It's a quantity that's completely described by its magnitude alone. No direction needed, or even meaningful.
Like temperature. 70 degrees, you don't ask which way.
Yeah. Exactly. Or mass. 5 kilograms. That's it. Fully defined.
Okay. Intuitive scalar. Just a number, a magnitude, no direction. Intuitive vector, magnitude with a direction. Easy enough.
Seems so.
But here comes that semantic ambush we talked about, that listener paradox. We use scalar for the temperature value, the number itself, but we also use it for the operation, scalar multiplication, taking a vector and just making it longer or shorter, scaling it.
And that's the linguistic trap. That's where the inertia of physics history kind of bites us. Because if you then hear scalar field, especially in quantum mechanics, and you're stuck thinking scalar means operation, you imagine this bizarre map where every point in space is just telling you to stretch this or shrink that.
Like a field of commands.
Yeah.
Which makes no physical sense.
Not at all. So we absolutely have to pry apart the object from the action it performs.
Okay. We need to dissect this word scalar properly. Untangle those 3 different meanings.
Right. Let's tick them off. We need to go from that simple intuitive idea to the really deep meaning that modern physics relies on.
Okay. Definition #1. The intuitive scalar, we just did that. Magnitude, no direction. A plain number. Temperature, mass. Foundation laid.
Check. Now, definition #2, the algebraic scalar. This is where we tackle that linguistic confusion, the scalar multiplication thing.
Why do they call it that? If it's confusing, why stick with it? Wouldn't physicists invent a better word?
You'd think so, but it's mostly history and, well, laziness maybe. When vector math was getting formalized, back in the 19th century, multiplying a vector by a plain number was seen mostly as scaling the vector's length.
Ah, making it bigger or smaller.
Exactly. So the number doing the scaling got called a scalar. It was just shorthand. And it's stuck. We're kind of stuck with the tradition, even if it confuses people now.
So the number itself, like the number 3, that's the object. The action of multiplying by 3, that's the operation. But the object gets named after its most common job.
Precisely. Let's use that analogy again. Think about a driver.
Okay, the person driving a car.
Right. The driver is the object, the person. But their name comes from the operation they perform driving. Now, if you talked about a field of drivers, you'd mean like a map showing where all the drivers are located, right?
Yeah, not a map of the act of driving itself.
Exactly. So in the same way, a scalar field has to be a field of values, these directionless numbers. It's a map of the objects, the scalars, not a map of the operations scaling.
Okay, that clears up the language trap nicely. Phew! So the confusion was just words getting tangled. But now we get to the really important bit, the physics meaning. Definition, #3. The formal scalar.
This is the big shift. Physics, especially modern physics, stops defining things just by what they are intrinsically, like it's a number. Instead, it defines things by how they behave, specifically how they transform when you change your perspective.
How they transform, like how they change when I look at them differently. That sounds abstract.
It is, but it's fundamental. Think of it as the invariance test. Imagine you measure something. Then I measure the exact same thing at the exact same spot, but maybe I'm using a different set of coordinates, like I've tilted my head, rotated my viewpoint.
Okay.
Whether we agree on the value we measure tells us what kind of quantity it is, formally.
Let's use temperature again.
Yeah.
I measure 70 degrees right here.
Yeah.
Then I tilt my head, rotating my mental XYZ axis. Do I still measure 70 degrees at that exact point?
Yes, you do. The value itself, 70 degrees, is invariant under that rotation. It doesn't change.
Yeah.
That is the formal, rigorous definition of a scalar in physics. It's a quantity whose value stays exactly the same no matter how you rotate your coordinate system. That's what having no direction truly means at this deeper level. Its value doesn't depend on any direction or axis you define.
Okay, so all observers, regardless of how they're oriented in space, agree on the scalar's value at the given point.
Precisely. Now contrast that with a vector. Think about wind again, a steady breeze blowing across the room. If you set up your coordinates north and east, you might describe that wind as, say, 5 units east and 5 units north.
Right, its components.
But if I rotate my coordinate system by 45 degrees, I describe the exact same physical wind very differently, maybe as 7.07 units straight along my new north axes.
Yeah. The description changes, even though the wind itself didn't.
Exactly. The vector's components, its mathematical description, transform in a specific, predictable way when you rotate the viewpoint. A vector transforms non-trivially. A scalar transforms trivially, meaning it doesn't change at all.
Transformation is everything. So the ultimate definition comes down to whether observers agree under rotation. But you did something even deeper before. The Lorentz scalar. What's that? What does relativity add?
Yes. The Lorentz scalar takes this idea of invariance, of observers agreeing, and kicks it up a notch. It's not just about rotation anymore.
What else is there?
It includes Lorentz transformations. These describe how things look when you change your velocity relative to what you're measuring. We call it a boost.
A boost, like speeding up.
Yeah, or just moving at a different constant velocity. In everyday Newtonian physics, if you measure the mass of a baseball standing still, and I measure it while flying past at high speed, we'd assume we get the same number for its mass.
Seems reasonable.
But Einstein's special relativity changed everything. We know moving clocks run slow, moving rulers shrink. Measurements depend on relative motion.
Time dilation, length contraction.
Right. So the math for transforming measurements between observers moving relative to each other, the Lorentz transformations, is more complex than just rotation. A Lorentz scalar is a quantity whose value is invariant, unchanging, not just when you rotate, but also when you boost to a different velocity.
Wow. So everyone agrees on its value, no matter their orientation or their speed.
That's the idea. Mass itself, like the rest mass of an electron, is a prime example of a Lorentz scalar. No matter how fast you're moving relative to an electron, you will always measure the same value for its fundamental mass. Its energy or momentum might look different to you, but its mass stays the same.
That's an incredibly strong condition. A truly fundamental absolute value within the rules of the universe.
It is, and that kind of scalar, the Lorentz scalar, is what we mean when we talk about a scalar field in fundamental physics, like the Higgs field. It's a map of these absolute directionless velocity-independent values.
Okay, definition #3, the formal Lorentz invariant scalar, is the one that matters for the deep stuff.
Got it.
Got it. Now what about the other half of the term, field?
Right. The word field has a similar split personality. There's the abstract math meaning, and then there's the physical meaning physicists use every day.
Let's start with the math one. Definition #1, the algebraic field.
This is purely abstract algebra territory. When a mathematician talks about, say, the field of real numbers or the field of complex numbers, they're not talking about space.
No. What are they talking about then?
They mean an abstract set of numbers, like a collection, that follows very specific rules for arithmetic.
Like what kind of rule?
Well, basically, you need to be able to add, subtract, multiply, and divide any two numbers within that set, and the answer you get has to also be in the set. That's called closure. Plus, the operations need to behave nicely. Associative, commutative, distributive laws need to hold.
Okay, so it's like a self-contained toolkit for doing math.
Yeah.
A box of numbers where the arithmetic always works.
That's a good way to put it. A supply closet for numbers, totally disconnected from physical space or time, just an abstract structure.
So if someone just said a field of scalars, they could technically mean this abstract set of numbers that obey math rules.
They could, in a pure math context. But that's almost never what a physicist means. Which brings us to definition #2, the physical field, like the Higgs field or an electric field.
Okay, what's the essential definition here? What makes it physical?
A physical field is fundamentally a function. It's a mathematical machine that assigns a specific physical value, some measurable property, to every single point in space and time.
A map, basically.
Exactly. It's a map. You give me the coordinates location, x, y, z, and time t, and the field function spits out the value of whatever property it describes right there, right then.
That map idea is super helpful. Let's use the weather map analogy again. It really clarifies the different types of physical fields.
Perfect. Okay, imagine you're looking at a weather map showing temperature contours or maybe air pressure isobars.
Right. Lines connecting points of equal temperature or pressure.
What kind of field is that displaying?
Well, at every location on the map, it gives you one number, the temperature value or the pressure value. No direction involved. So that's a scalar field.
Precisely. And because those values are scalars, formal definition #3 scalars, you can rotate the map, look at it sideways, and the temperature reading at a specific town doesn't change.
Okay, clear. Now, what about the wind map? The one with all the little arrows showing wind speed and direction?
Uh-huh. Now, at every point on that map, you're not getting a single number. You're getting an arrow, a vector.
Right, telling you both how strong the wind is, magnitude, and which way it's blowing, direction.
So that's a vector field. More information packed into each point. And crucially, if you rotate that map, the description of the wind arrow at a specific town, its components relative to your map axis, will change.
Got it. So the field part in physics always means the map, the function assigning values to space-time points, and the word before it, scalar, vector, or something else, tells you what kind of mathematical object is being assigned at each point.
Exactly. You've nailed the distinctions. We've taken apart the confusing words. Now we can put them back together the right way and see how this helps us classify reality itself.
Okay, synthesis time. Let's put scalar and field back together using the right definitions. A scalar field is what?
It's not a map of operations. It's not just an abstract set of numbers. It is a physical field, meaning the space-time map function, that assigns a formal scalar value, meaning a Lorentz invariant, directionless number, to every single point in space and time.
So, bottom line, it's just a map of these very specific, rotationally invariant, directionless numbers filling the universe.
That's exactly it. And understanding that focusing on how things transform, especially under rotation, lets us understand the fundamental way physicists categorize everything in the universe. The standard model structure relies on this.
Right. You said everything fundamental particles, fields, falls into one of three families based purely on how it transforms when you rotate space. And this property is called spin, right? Intrinsic angular momentum.
Correct. It's a quantum mechanical property, but its roots are in this classical idea of rotational transformation. Let's lay out the families.
Okay. Family 1, spin arrow, the simplest one.
This is the scalar family, the defining feature. Its value is totally invariant under rotation. Spin the system, rotate your view. The value assigned by the field at a point doesn't change one bit. It transforms, as we say, trivially.
And the Higgs field belongs here.
The Higgs field is the prime example of a fundamental spin-zero scalar field. Temperature is a non-fundamental example. Simplest transformation behavior possible.
Okay. Next family. Family 2, spin 1.
This is the vector family. These are things that transform under rotation exactly like you'd intuitively expect an arrow or a vector quantity like wind direction to transform.
Meaning its components change depending on your viewpoint.
Yes, according to the standard mathematical rules of rotation. And crucially, if you rotate the system by one full circle, 360 degrees.
It comes back to exactly how it started.
Mathematically, yes. Its description returns precisely to the original. This family includes the force-carrying particles, the bosons, photons for light and electromagnetism, gluons for the strong nuclear force, the W and Z bosons for the weak nuclear force.
Okay, that seems normal. Intuitive, even. 360 degrees gets you back home.
It does for spin 1. But now we get to the really weird stuff, the deep quantum
In
secret.
family 3, spin 12, this is the spinor family.
Yes, and this family contains all the fundamental particles of matter, everything that makes up you, me, the stars, the planets, electrons, neutrinos, all the quarks. They are described by mathematical objects called spinors.
And how do they transform under rotation? Is it like vectors?
Not at all. This is where intuition completely breaks down. A spinor is, mathematically speaking, a sort of double-valued representation of rotation.
Double valued. What does that mean?
It means that if you rotate a system containing a spin 12 particle by 360 degrees, it does not return to its original mathematical state.
Wait, what? How is that possible? If I spin an electron, or myself, 360 degrees, I'm back facing the same way. Everything looks identical.
Spatially, yes. The orientation in space is the same. But the internal quantum state, the complex number wave function that describes the electron mathematically, has changed. It picks up a minus sign, it flips its phase.
It becomes negative itself. just from one rotation.
Mathematically, yes. It's like it's turned upside down in some abstract internal space, even though it looks the same externally. It somehow remembers the rotation path it took. It's sensitive to the topology of rotation, not just the final angle.
Whoa, okay, so how do you get it back to its original state then?
You have to keep rotating it. You need to go around again another 360 degrees. A total of 720 degrees of rotation is required to bring a spin 12 spinor back to its true original mathematical state.
720 degrees. 2 full turns. That is deeply strange. I know the analogy people use is the Dirac belt trick, or sometimes holding a plate.
It's the best way to get a physical feel for this topological weirdness, absolutely. It bypasses needing the complex math of group theory like SU2 versus SO3.
Okay, walk me through it. Let's say my arm is the spinor, the underlying system.
Right, the arm represents the particle's state, and maybe your hand, holding a plate flat, represents its orientation in space, like a vector pointing up.
Arm out, palm up, plate level, vector points up. Now rotate my hand 360 degrees, keeping the plate level.
So the plate, the vector orientation, comes back to pointing straight up after 360 degrees.
Okay. Done it? Yeah, plate looks the same back where it started. But look at my arm. It's horribly twisted. It's definitely not back in its original relaxed state. I can't untwist it without moving the plate again.
Exactly. The vector part, the plate's orientation, completed its cycle at 360 degrees. But the spider part, your arm's state, did not. It's knotted up. It remembers the twist.
So now what?
Keep going. Rotate your hand another 360 degrees in the same direction, keeping the plate level.
Okay, rotating again. 360 plus 360 is 720. Whoa!
What happens to your arm?
It untwisted itself. As I completed the second full turn, the twist just disappeared. My arm is back in its original relaxed position effortlessly.
And that is the magic of spin 12. It takes 720 degrees for the underlying state to return to normal. That visualization perfectly captures the topological difference. Matter particles are woven into the fabric of space-time geometry in this incredibly subtle, non-intuitive way. They carry a memory of rotation that vectors and scalars don't have.
That's incredible. So this classification, spin 0, spin 1, spin 2, it's not just some arbitrary labeling. It's dictated by the fundamental geometry of rotations in our universe.
Absolutely, it's a rigid framework. And it's this framework, this classification based on transformational properties that leads directly to why the Higgs field had to be a scalar.
Okay, so we've firmly established the Higgs field is spin 0. It's a Lorentz invariant scalar field. It assigns one of those directionless absolute numbers to every point in space-time. Now connect this back to that revolutionary weird fact about the Higgs. Its value isn't 0, even in empty space.
Right, the non-zero vacuum expectation value, or VEV, this is the absolute core of the Higgs mechanism. For almost every other fundamental field we know, like the electromagnetic field, the gluon field for the strong force, the state of lowest possible energy, what we call the vacuum or empty space, corresponds to the field having a value of 0 everywhere.
Makes sense. Lowest energy means nothing's happening. No field activity, no forces, just 0.
But the Higgs field is the exception. Its potential energy landscape isn't a simple bowl with the minimum at 0. It's shaped famously like a Mexican hat or the bottom of a wine bottle. There's a peak at 0, but the lowest energy state isn't there. It's down in the circular trough around the peak.
Meaning the absolute minimum energy state, the true vacuum, corresponds to the Higgs field having some non-zero constant value everywhere.
Precisely. The vacuum is not empty in the Higgs sense. It's permeated, saturated with this constant background Higgs field value. And it's this non-zero value that particles interact with, which gives them their mass, like wading through treacle.
Okay, but for this whole picture to work, for our universe to make sense, it has to obey a really fundamental principle of cosmology, right? The symmetry of the vacuum.
The absolute bedrock principle. The vacuum state must be symmetric. It has to look the same to all observers, regardless of their location or orientation.
Meaning no special places, no special directions in empty space. It must be homogeneous, same everywhere, and isotropic, same in all directions. If you had a preferred direction, like a giant cosmic arrow pointing that way.
Our entire understanding of cosmology, the expansion of the universe, everything falls apart. The laws of physics might be symmetric, but the vacuum state must also respect these spatial symmetries.
So here's the potential clash. We need a field that has a non-zero value everywhere in the vacuum to give mass. But the vacuum must remain perfectly symmetric, isotropic, no preferred directions. How do we reconcile that using our spin classification?
Let's do the thought experiment. Imagine the field responsible for mass wasn't spin 0. What if it was, say, a spin 1 vector field?
Okay, so a field of little arrows at every point in spacetime.
If that spin 1 field needed to have a non-zero value everywhere in the vacuum to give mass, what would that look like?
Well, those arrows would have to point somewhere,
Hmm.
right? Even if they all pointed the same way consistently.
Exactly. You'd inevitably end up with a vacuum filled with tiny vectors, all aligned in some particular direction. A universal up or northeast built into the fabric of empty space.
And the second that happens, poof, there goes
Good.
isotropy. You've just defined a preferred direction in the universe.
You've broken the fundamental symmetry of the vacuum. A vector field simply cannot take on a constant non-zero value throughout space without violating isotropy. It has to average to zero in the vacuum to preserve that symmetry.
Which is why the photon field, spin 1, and gluon fields, spin 1, are zero in the vacuum, and photons and gluons are massless.
Correct. They respect the symmetry by being zero. So this forces our hand. It leads us to an unavoidable, profound conclusion about the nature of the field that does give mass.
But the only way out.
The only possible way for a fundamental field to permeate all of space with a constant, non-zero value without creating a preferred direction, without violating the essential symmetry of the vacuum.
Is if that value has no direction associated with it.
It must be rotationally invariant. It must be the same for all observers regardless of orientation. It must be a Lorentz scalar.
It must be spin zero.
It's the only option that works. The Higgs field settles into its non-zero minimum value in the vacuum trough. This is the famous spontaneous symmetry breaking, SSB. The underlying laws might have a symmetry, but the ground state, the vacuum solution, breaks that symmetry by picking a value.
Like the marble rolling off the symmetric hill peak and settling at one specific point on the rim. That point breaks the rotational symmetry.
Exactly. But the crucial thing for the Higgs is that because it's a scalar, spin zero, the specific non-zero value it settles on is just a number. It doesn't point anywhere. It breaks an internal abstract symmetry of the particle physics interactions, called the electroweak SU times UN symmetry, but it crucially preserves the geometric rotational symmetry, isotropy, of space-time itself.
And it's that act of the field settling into that non-zero scalar value, breaking the internal symmetry, that gives mass to other particles, like the W and Z bosons.
That's the mechanism. Briefly, the symmetry breaking predicts massless particles called Goldstone bosons. But in gauge theories like the Standard Model, these Goldstones get sort of eaten by the force carriers associated with the broken symmetries, the W and Z bosons. This process gives the W and Z the extra polarization state they need to be massive. And the leftover excitation of the Higgs field itself, the ripple in that non-zero value that isn't eaten, that's the Higgs boson particle we discovered.
Wow. So the confusing word scalar, once we formally defined it through invariance and transformation, became the absolute key. Its spin zero nature is not just a label. It's a fundamental requirement for a universe with mass that still looks the same in all directions.
Logic locks into place. The scalar nature of the Higgs isn't just incidental, it's necessary for the consistency of the cosmos as we observe it. Hashtag tag outro.
That was quite a journey, from getting tripped up by high school definitions of scalar all the way to the spontaneous symmetry breaking of the vacuum and the necessity of spin zero. My head's clearer now.
It really connects the dots, doesn't it? For me, the most profound thing to really sit with is that realization, how we classify fundamental reality spin 0, spin 1, spin 12, isn't based on what things are made of or what they look like statically. It's all about how they respond when we change our perspective, when we rotate or boost.
Yeah, it's all about symmetry and invariance.
Yeah.
That foundational principle dictates the existence of the very field that gives things mass. It's pretty awe-inspiring when you think about it.
Totally.
And bringing that kind of clarity, connecting those deep ideas, that's exactly what we aim for in these deep dives.
Yeah.
We really hope this discussion untangled the scalar field confusion for you and gave you that powerful geometric reason for why the Higgs has to be the way it is.
And you know, we talked about some really complex visual ideas today. That Dirac belt trick, the 720-degree rotation for spinors, it's the kind of thing that just screams out for a visual aid.
Oh, definitely. Which brings us back to what we mentioned at the start. If you want to help us take these deep dives to the next level with video to actually show these transformations,
The best way you can help is by hitting that subscribe button and maybe sharing the show with a friend or two.
we're really aiming for that 1,000 subscriber mark. That's the key to unlocking the funding we need for the kind of sophisticated tools that make high-quality video possible without bogging us down.
Yeah, specifically, we really want to get our hands on the Mosaic AI video editor. We mentioned it before, Mosaic.so. It's just fantastic for automating the creative side. We feed it the audio link.
And it generates relevant, beautiful AI visuals, braille animations. It basically helps us turn this conversation into a compelling video much, much faster. It handles so much of the production grunt work.
It really streamlines the whole creative process, an amazing tool.
So please, if you enjoyed this, if you got something out of it, take that quick second, hit subscribe, help us get Mosaic AI and start making these videos happen. We really want to do it.
We do. Okay, until next time.
Keep searching.